So we're going to look at mass and moles and stuff like that. So a very, very brief recap that if we're looking at, there's two things that we need to consider, AR and MR. And AR is the atomic, relative atomic mass, and I'm not going into the details of that, but relative atomic mass is the top number in your periodic table. That tells you how many protons and neutrons are in the nucleus of something, and then the MR is the relative molecular mass. So there's a difference between individual atoms and then molecules. So the individual atoms would just be sort of a hydrogen atom on its own, but then if we had a water molecule, and let's see, water molecules, so oxygen is 16 and hydrogen is 1. We've got 2 lots of hydrogen. So we've got, let's see, 2 lots of hydrogen, which equals 2, and then 1 lot of oxygen, which is 16. And we add them together, we get 18. So that would be the MR, the relative molecular mass, or the mass of the molecule. Now, the reason I'm sort of focusing on this is because there are certain things you can do with this very basic concept. There's certain things you can do later on to pull yourself out of trouble if you get a really tricky question. Anyway, the one sort of addition to this, and hopefully you should all be aware of this, you can actually work on percentage mass. Now, the percentage mass is basically how much sort of each element contributes to the overall mass. So if we were to look at, say, hydrogen, we've got 2 out of the 18 is hydrogen, and then we look at oxygen, which is obviously 16. 16 out of the 18 is oxygen. So by the time you've done that and you put it into the calculator, you come out with, I think it's about 0.1 and then 0.88. Let me just go back and make sure that we, poor Isabel. Is she in? She's in. Success, Isabel. Well done. This is really important. So these are decimals, and obviously to get the percentage, the overall percentage, we just times by 100, and hopefully you should be able to do that in your head. That, you know, by the time we times these by 100, it would be roughly 88% and roughly 11%. I'll come back to that later on in one of the questions that we need to look at, because I think, as I say, this can get you out of a hole massively so. So just before I move on, does anyone, and I'll have to have a look at the comments, does anyone, is anyone struggling with that? I don't think there's any comments that I can see. Meeting chat. If no one's struggling, I can move on. If you are struggling, now's the time to tell me. And I know it's difficult to admit that, but that was really, really quick that I just sort of zipped through. So if you are struggling with that, you need to tell me now, or send me a message in the chat and I can sort of catch up with you later on. Okay? So we'll move on now. One of the things I think that really sort of doesn't help is the use of the word mole. I think my pen's a little bit big. I'm going to drop it down there. The use of the word mole. I think mole makes it really difficult for things. Okay. Let's keep the rainbow. So Lulu. Here comes Lulu. So this word mole, it can be quite confusing. There's a couple of definitions for a mole. So one mole, oops, a daisy, is the AR or MR in grams. Okay, so that's one definition. I think I might go back to the to this bigger pen, big fat one. There we go. So 1 mole is the AR or the MR in grams. So 1 mole of water, so H2O, we've saw it before that the MR is 18. Well, 1 mole of water would weigh 18 grams, have a mass of 18 grams. The other sort of interesting thing is that 1 mole of anything and it doesn't really matter what it is. 1 mole of anything contains 6.022 times 10 to the 23, and it depends, atoms or ions or molecules, and we just call them species, okay, because they can be anything. It depends whether, if it's a metal, it would be atoms. If it was, if it was an ionic compound, it would be the different ions in there. If it was water, it would be molecules. So in 18 grams, i.e. 1 mole of water, we would have 6.022 times 10 to the 23 moles of water. And what that means is, let's see if I can just drag that. Oh, brilliant. What that means is it's a huge number. I think it's, so don't hold me on this. Let's see, 1, 2, 3, 6. Something like that. Throw another one in there. So it's a huge number, really huge number. And what it means is that it gives you the idea that molecules and atoms and ions are really, really small, because 18 grams of water is not that huge an amount of water. It's sort of maybe a third of a test tube. So so in a test tube, sort of the third of the test tube of water, you would have that many water molecules. And I think that's enough. I think the word mole and this huge number is enough to just spook people. It sort of, it puts people off, but you shouldn't be put off. So what I'll try and do is I'll try and relate it to something. So if we've got, let's say, I think that's how you spell it, quail eggs. Quail eggs are sort of little spotted eggs that tiny fowl lay. So these quails are really small. And then we can have a chicken. We know about chicken eggs. Chicken eggs are bigger. And then, let's see, what can we have then? Ostrich. An ostrich egg is huge, okay? But we know, say, if we had, let's see, a quail egg, and a chicken egg and an ostrich egg, if I said to you, we're going to have a dozen. Now, you know what a dozen is. A dozen is 12. And if I said to you, we've got 1 dozen, how many eggs would we have? Well, you would be able to say 12. If I said to you, we've got 4 dozen, it would be 4 lots of 12, so that's 48. If I said to you, we've got half a dozen ostrich eggs, well, you know that half of 12 would be 6. And I think what I'm trying to say is that this word dozen, you're familiar with. You know what a dozen is. You know what, a dozen eggs or a dozen whatever hamburgers. You know what that is. And if I said to you, we've got 2 dozen, you'd know it was 24. So you don't really have this issue with the word dozen, and it's probably because you've been brought up with it from a very early age. And all I'm going to say to you is that if we know in a dozen we've got 12, I'm just going to say we're going to use this word mole. So instead of a dozen, we're going to use mole, and in a mole we've got 6.022 times 10 to the 23. So if I had 1 mole of anything, I would have not 12, because 12 would be a dozen. 1 mole would be 6.022 times 10 to the 23. And if I had 4 moles, I would have 4 times Avogadro's number. 4 lots of 6 is what? It's about 24, so it would be 2.4 whatever times 10 to the 24. And if I had half a mole, so 0.5 of a mole times that, it's just the same as half a dozen would be 6. Half a mole would be half of the 6.22 times 10 to the 23. So that would make obviously 3.011 times 10 to the 23. So what I'm saying is, don't be put off by the word mole. And some of you may be sitting there thinking, I'm not put off by the word mole, but I know a lot of you would be. It's enough to sort of spook you, this idea of the word mole and that huge number. You very rarely have to explain it, to be honest, and you don't really have to do many calculations, but they might just ask you, if you've got 2 moles of something, how many, 2 moles of iron, how many atoms of iron would you have in it? Well, if we go back and we sort of think, 1 mole of anything would contain this number. So if you've got 2 moles, you've got double that number. Once again, if anyone's got any sort of comments or problems, feel free to stop me, okay? So I'm going to move on. I think again, this is another thing where students get confused, is when you need to apply the number of moles. The number of moles is just an idea of how many reacting particles you have. And again, we don't really consider these huge numbers. We just get ratios. We just sort of think about molar ratios. So let's see, what can we do? I'm going to give you 2 things. I'm going to put down the number of moles. Hopefully you'll be all right with that sort of hashtag. It's an old way of writing number. So the number of moles can either equal the mass of something in grams divided by the MR or the AR, depending on what you're looking at. And then we've got a different way of calculating number of moles. Number of moles in solution is molarity times volume in decimeters cubed. You're probably being shown this slightly different ways by your teachers in school. You can, if you're happy with what you're doing, use the method that you're working with. I will go back and I'll look at this thing another time. If there is demand to look at sort of calculate moles in solution and looking at titration questions, if the demand is there, and you can leave me messages on Teams or whatnot, if the demand is there, I'll put a session on for calculating sort of moles in solution and then applying them to titrations. But for now, what we're going to look at is this top one. The number of moles is the mass in grams divided by the MR. Okay, so we will go back to this in a few minutes. So what I'll do is I'll give you a quick example of how we can apply molar ratios. Okay, so molar ratios are just the coefficients at the front of equations. So we can have CH4 plus 2O2. Okay, so no number in front of something just means 1, and then that number there, obviously that coefficient in front. So that would be a 1 to 2 ratio, which means that for every mole or molecule of methane, we would need 2 molecules of oxygen. Okay, again, you can involve Avogadro's number if you want, but I don't think there's any need because I think it does become a little bit confusing. Anywho, this molar ratio is really important. That's the only sort of idea you have to get through your head. So I'm going to get rid of this. We'll have an example. Let's see. I'm going to go back up to this. Sorry, guys. So well, I've pressed the button on the side of my pen. I need to come out of that. That looks a bit weird. So I'm going to do a different one. Let's see what we've got here. So what I'm trying to show you here is that we can make it's very difficult to draw that. It's better if I draw it on the board, you know, when I'm in the class. It makes it easier. So what I've tried to make here, you should be able to see. I apologize for the drawing. You should be able to see here that I've made a sandwich, okay? So it's a cheese sandwich. It's not balanced. Why isn't it balanced? Well, if you look on this side, we've got 2 pieces of bread and 1 piece of cheese. We've got 1 piece of bread here, but we've only got, 1 piece of cheese here, but we've only got 1 piece of bread. So to balance that out, I put this number 2 in front of it, which means I've got 2 lots of bread I don't need to draw 2 pieces of bread out, but I've got 2 lots of bread. So 2 lots of bread, 1 piece of cheese would make 1 sandwich. So the molar ratios, or the ratios here, would be 2 to 1 to 1. So I would need 2 pieces of bread for 1 piece of cheese, and then I could make 1 sandwich. Okay, so that's 2 to 1 to 1. And this is the basis of a lot of the maths that you're going to see in chemistry. Is this really simple concept? So if I said to you, let's see, each piece of bread was maybe, how much does bread weigh? 30 grams, and that's 15 grams. And let's see, so if we've got 2 pieces of bread and 15, so that would be what, 75 grams. Now, we know that the conservation of mass tells us that we've got to have the same sort of number of atoms on each side of the arrow. So i.e. that will end up with the same mass. So why have we got 75 and only 45? Well, we need 2 lots of that, don't we? So 2 times 30 would obviously be 60, plus the 15 would then equal the 75. Now, where we apply this idea of molar ratios is that we can use the MR, the moles equals mass over MR. It's a bit, as I say, just go with me, because this will be helping some people. So I'm going to say that, what was it? Each piece of bread was 30 grams. 1 piece of cheese was 15, and this was 75 grams. Okay? So, let's see. If I wanted to make, I don't know, for whatever reason, 5,000 grams of the sandwich, I'm going to get my calculator here, because I'm going to look like an absolute turnip if I get this wrong. So I'm going to get my calculator. So the way to work this out, literally how many sandwiches that will yield. So how many moles or how many sandwiches that will yield? 5,000 divided by the 75, because that is how much 1 would weigh. So how many would we have in 5,000? So 5,000, just bear with me, divided by 75. And that's going to give us 66.66 sandwiches. Okay. Now we need to think of the molar ratios. So that was 1 to 1 to 2. Okay. So if I've got 1 to 1 ratio, we can just quickly put over the number of moles, for want of a better word, 66.66. I would need 66.66 pieces of cheese for these 66.66 sandwiches. How much that would weigh we'll come to in a minute, but to make 66.66 sandwiches, I would need to have 66.66 pieces of cheese, because it's 1 piece of cheese for every sandwich, it's 1 to 1. But I'm going to have to double it to get the number of pieces of bread, because we've got this 2 to 1 ratio. So it's going to be 2 lots of that. So 2 lots of the 66.6. I'm going to literally times it by 2, because again, I don't want to look like an idiot. 133.33. And that's how many moles of or pieces of bread we would need to make 66.66 sandwiches. We would need 133.33. Okay. Now, we need to find out sort of how much that would weigh. Now, here's the thing, and you can do this. We're still going to use this equation. Mass over MR would give us moles. Okay. Let me just go back to that. Oh, Lulu, come on. So we're going there. Mass divided by moles would give MR. But if we go the other way and we go moles, and then we're looking at MR, if we times it by the MR, that will give us the mass. So going down here on this side, if we mass divided by MR would give us moles. Well, if we go up the other way, it's moles times mass. Moles times MR will give us the mass. So if we think now, what is the mass of each piece of cheese? Well, for this one, it's 15, isn't it? So 66 times 15. I'm having to do this on my phone because it'll let me calculate it and work. Times 66.66. Ooh. So that would give us 999.9 grams. Okay. Which looks interesting. Yeah, this should work out. And then if we do the same for the other one, 133.33, well, each piece of bread is 30. We've already done our conversion here. We've already converted the 2 to 1 to 1 or the 1 to 1 to 2. We've already done that when we've done the 66 to 66 to 133. So all we need to do is just take this 30 grams. So if we do 30 grams, clear that, and we times it by 133.33, we should come out with 3,999.9. I'm not the best mathematician in the world, but I could tell you that by the time you round this up to 4,000 and 1,000, that would equal the 15,000 on that side. And your sort of your task in GCSE chemistry is pretty much based on that, based on your ability to recognize the molar ratios, work out the number of moles that you can, adjust for the molar ratios, and then work out the masses that you will produce. Okay, it's fairly straightforward. Well, I know I'm saying that, but once you get the hang of it, once you realize what's going on, it should make sense. I like the cheese sandwich analogy because, as I say, it does work well because we can relate to that. We can relate to the cheese sandwich, or any sort. If you don't like cheese, put some ham or chicken on or something. I'm not bothered. But we can all relate to that, can't we? We that's tangible, and I think it's easier to sort of get your little toehold into the chemistry based on that. And all you've got to do, as I say, it's this thing, the mass over MR will give you the number of moles, and they will always start a question, and they would have to give you the ability to work something out. So in this case, the number of moles of something, and then you just go back and you just apply the same thing. So let's have a look at another example. I'll do an example of, so one that we saw before. So methane will burn in oxygen to produce, and you should know this, carbon dioxide gas and water. So one of the questions you might get asked is, how much carbon dioxide gas would be produced if we burnt a certain amount of methane? And we're just going to pick the numbers at random, but it's based on the same thing. So if I said to you, let's see, we can just pick a number out of the air, 60 grams of methane. Well, if you remember, and I'll sort of try and squirrel it down the side here, we're going to have mass over MR, and that would give us the number of moles, okay? And that's what we want to get. That's the first thing we need to find out. Here we go, it's the rainbow pen. The first thing we need to find out is the number of moles. So if they just give us 60 grams, that's enough for us to be able to work out everything. So the number of moles of oxygen we will need, the number of moles of carbon dioxide we will produce, the number of moles of water we will produce, and also the masses. Because as soon as they give you grams, you should be thinking mass. Okay, so the mass in grams over the MR will give us the number of moles. So all we need now is to work out the MR of this. Now, they might give you it, they might give you this, but this is going to be, so a quick recap now, we've got 12 and 1. So one lot of 12 is 12, and 4 lots of 1 is 4. So 12 and 4 will give us 16. Okay, so we're now going to work out the number of moles of the methane that we started with. So it's 60 divided by 16. And that is, let's see, what pen should I use? I'm going to go for the green pen. That's given us 3.75 moles of the methane. Okay, and I'm trying to keep everything sort of in a line underneath so we can follow this. The next thing to do, because we've worked out the number of moles, the next thing to do is try and look at the molar ratios. It's a 1 to 2 to 1. Oh, hang on. To 2 ratio. Okay. If you're not sure about this, I can sort of help people out with this, but basically we've got one carbon atom in the methane molecule that will be able to produce just one carbon dioxide. We've got 4 hydrogen atoms in the methane molecule that will be able to produce 2 water molecules, because H2O, there's 2 hydrogen atoms in the molecule, so we can make 2 molecules. Okay, so the ratio, going back to this, it's a 1 to 2 to 1 to 2. So what I would do is I would just pick out the easy ones. I'm going to take this methane and the carbon dioxide is 1 to 1. So therefore, if that's 3.75, this has got to be 3.75. And then we need to double it up. So when we double this up, we're going to get sort of 3.75 times 2, which equals 7.5. And we don't need to do any calculation here, because if that's a 1 to 2 to 1 to 2, it will be 3.75 to 7.5 to 3.75 to 7.5. And if you remember what we did sort of coming down this way, which was our mass divided by MR, would give us the number of moles. Then when we go back up the other way, we just times everything by the MR. So we're going to put the MR of these things in. So O2 is 32. It's 2 lots of 16. It's 32. Don't forget, we've already adjusted for these 1 to 2 to 1 to 2 ratios. We've already done it with the number of moles. So there's no need. Some people think that we're going to have to put in 64 here because it's going to be 2 lots of O2. It's not. We've already adjusted down here. Okay. So 32, carbon dioxide is obviously 12 and 2 lots of 16. 2 lots of 16 is 32 and 12 is 44. And then water, as we saw before, is 18. Okay, so the question might ask, how much carbon dioxide do you make? If it's just asking about carbon dioxide, just do carbon dioxide. But we'll do them all because it's good practice. Let's see, so I'm going to have 7.5 lots of 32. So 240 grams. We're going to go for 3.75 of 44, which is 165. And then we're going to go for 7.5 of 18, which is 135. Okay, so these are all in grams. And like we did before, by the time you add this together, so 60 and 240, 300. 165 plus 30, 135 is 300. So they should balance out. That's one way you can check that all your sort of sums are right. So it's essentially exactly the same as the sort of cheese sandwich thing. If we just go mass divided by MR will give us moles. So if you go down that way, and then if you go up the other way, you just multiply moles times MR. Okay. Does anyone have any questions at this point? Because I've been going on now for about... Yeah, it should be 2 water CP. I got onto that. Thank you very much for that. Well spotted. Does anyone have any questions on this at this point? Okay. So what we could do, I'll try and look at an example from a past paper. Okay, so I'm going to try and insert a PDF here. Let's see if we can get this on the go. Just to basically, I'll show you how we can do it. There's sort of loads of ways you can do these questions. Here we go. I've got question 1. Let's open this up. I don't know how this is going to... Oh, come on. There we go. hopefully you can all see that. It's a little bit squished. I probably should have just done a print screen and just cropped it or something. However, what we're going to look at, when you're doing this, you should sort of highlight what you can. This is an electrolysis question. It's part of the electrolysis thing that we looked at last week. I didn't have time to put this video on, but I'll do it now. So it's saying here, hopefully you can see this, calculate the mass of oxygen produced when 2,000 kilograms of aluminium oxide is completely electrolyzed. And they've given you these AR values. If they give you the AR values, I'm going to try and make that bigger, you know, folks. If they give you if they give you the AR values and a mass, they're basically wanting you to work out the number of moles. There we go. Do you think I could? Let's see. There we go. Let's give this a go. Oh. So if they give you the this might work. If they give you a mass and they give you the AR values, they're basically wanting you to work out the number of moles. So if we have 2,000 kilograms, we're going to have to divide it by, I know it's kilograms, and we should be dividing by grams. We should be using grams, but we can just keep it as kilograms because they want the answer in kilograms, so we can just use 2,000. So 2,000, so we need to know the the MR of the aluminium oxide. So in an exam, what you could be tempted to do is just annotate. We've got 2 lots of aluminium, which is 27. So we've got 2 times 27. We got 3 times 16, 3 lots of oxygen, that's 16. So that is 48. And then the 2 times 27 is, what would that be? 52. 54, is it? 54. Okay, so by the time you put them together, let's see, 54 and 48 is about 98, 102. Okay, so 2,000 divided by 102 should give you the number of moles. It's not really the number of moles because we're using kilograms, so it'll be, we need to times it by 1,000 to get the number of moles. But I'm just going to keep it as this, 19.608. So the next thing we need to do, that's the number of moles of the aluminium oxide that we have. We need to look here at the molar ratios. It's a 2 to 3. So we're actually going to get more moles of oxygen. The moles of oxygen are going to increase because we go from 2 moles of aluminium oxide to 3 moles of oxygen. But we don't really need to worry about the word moles or what we're doing. We just need to look at the molar ratio. So 2 of these becomes 3. So you can either do 3 over 2 or 1.5. Okay? So if we times that by 1.5, that will give us the number of moles of oxygen, which equals, what's that going to be? 29.412. Just going to get rid of that. Okay. So now we've got the moles of oxygen. And I know I've done this slightly differently. Now we've got them, I'll tell you what. Let's do it all again. I'm going to do this first. So the aluminium oxide, 2,000 over 102 would give us 19.608. We need to adjust for the molar ratios, so we need to times that by 1.5 to get the moles of oxygen. The moles of oxygen were therefore 29.41. Now we're going to times it by the MR of oxygen. So the MR of oxygen is 32. We know it's 32 because it's the 2 lots of the oxygen atoms, 16. We've adjusted for the molar ratio. So again, don't think it's 3 lots of O2. Don't think it's 3 lots of 32. It's not. So we've done that. So we're going to go back to the 29 times 32. And because we're going up, that will give us 941 point, say 18. Okay, that's the answer, 941. Because what have they used here? Okay, it's 941 kilograms. If you used 2,000 there, you would come out with a bigger number, 412, something like that. But all you'd have to do then, because you'd have 94118, you just have to divide by 1,000 to get it back into kilograms. So you basically pick what you're happy with. But if you think about it, if you start off with 2,000 kilograms of the aluminium oxide, it's only ever going to go down because we're separating the aluminium and the oxygen. So any number that's bigger than 2,000 is wrong, and it's going to be, in those ratios. This is the thing that I was talking about before, right at the start. There are things that we can do to help ourselves here. Now, I would look at this, and I would be more than happy if any of my students took this approach, which I've been repeating. You go down that way, and then if you're going back up, so you're down, divide, and going back up. I'd be more than happy if my students did that. But my students would actually pick up onto the fact that you can look at this, and in the aluminium oxide, we can do a percentage mass. So the percentage of oxygen in that is 48 out of the 102, which is basically, what are we looking at there? 48 out of the 102. It's going to be just under 48%, isn't it? So 48 out of the 102, 47. So that would give us 0.47 06. Okay, that's a decimal. I'm going to times that by the 2,000. So if I take that and times it by 2,000, I come out with 941.17. So I come out with the right answer, not by doing all this, but by just looking at it and thinking, well, how much of this aluminium oxide is actually oxygen? If you know that it's 47% oxygen, you can just take 47% of the original 2,000 kilograms would be your answer. So there's a million and one ways in which you can do this. This is a relatively easy one. Again, does anyone have any questions about that? Okay, so we're sort of coming up to time now on this. I've got another example if we're happy to sort of stay with this. I'm going to clear the canvas. I'm going to insert another PDF, and it's basically using the same thing that we've looked at before. There we go. So let's see. They give you a mass. This is the second. This is the second part of this question. So they're giving you another load of easy marks. Calculate the volume. 150 kilograms of chlorine gas at room temperature and pressure. Okay. They just say there that 1 mole of any gas is 24 liters. So basically, we need to find out the number of moles. But you know that because they've given you 150 kilograms. So 150 kilograms, I think we would need to work the number of moles out in this case. So it's going to be 150 kilograms is 150,000 grams. It's of the Cl. They've even given you the MR of the Cl, 71. You could work that out yourself, obviously. If we do 150,000 divided by 71, what will we come out with? We will come out with... it's about 2,112. Let me just check that. 50, 1, 2, 3, 71. Yeah, 2,112. That's how many moles we've got. Now, with 1 mole is 24 litres, then 2,112 moles would be 2,112 lots of 24, which will give us, should we just take the answer that we just got and times it by 24, and it would be 50, quite a big number, because we've got a lot of, we've got over 2,000 moles, 50,704, I think we go for. Okay, so I'm going to stop the sort of